so you can feel pretty confident it's going to go to 0. But you want to be, when these start getting weirder and you write just a few elements out, you can't make any grand predictions just from a few pieces. Because maybe it starts at 1, 1/2, 0.3, and then all of a sudden it's 10, 20, 80, based on how this thing is built up. So you can't tell anything just from writing a few elements out. You can't. And this one, it happens to be that they match up. How could I possibly tell what the limit of this is going to be? So the limit as n goes to infinity of this ugly looking thing. Who has a suggestion as to how to handle this thing? Now, we already have a feeling that it's going to go to 0, right? And we just want to kind of verify that it's going to go to 0. So this -1 piece doesn't really bother me. I don't care if it's bouncing around 0. I know it's going to go to 0, right?
What?
Yes?
Why do we think it's going to go to 0?
They keep getting smaller. And also, which one goes to infinity quicker? Adding 2 to n or raising 5 to the nth power? So what does that sound like I'm building up to? I'm looking at the rates of approach to infinity of each of these separately. What rule does that sound like I might want to use?
The one we just
L'Hopital's. The one that everybody tries to use too early in calculus, right? Because tutors very often, as a tutor, you want to do it because it's the easiest thing in the world, but if you haven't learned it yet, but we all know L'Hopital's. The one problem with trying to use L'Hopital's on this is what must be true, of course, about the top and the bottom. Because what does L'Hopital's have us do? Take derivatives. What do you think might be wrong? Why might these be bad for trying to do that? Are they differentiable? If I graphed this, would it look like just dots? Is that differentiable? I don't know if you guys remember, to be differentiable, you must actually have limits defined, and those are dots. I can't have any limits defined, can I? So here's the really nice thing that we're allowed to do. We're allowed to write the function that would be this with the n's replaced with x, right? Which, again, is one of those things that a lot of students are like, why even do that? Let me just do L'Hopital's directly to this. It's because of the fact that we got to follow these rules. So if I take the limit as x goes to infinity of this, and I'm just going to kind of ignore the negative piece. If it goes to 0, that negative piece doesn't mean anything to me. Are you guys cool with that? If it doesn't go to 0, that negative piece is important then all of a sudden. It might be oscillating then, right? -1, 1, -1, that's no good. But now I can apply L'Hopital's. So how's that going to work? If I apply L'Hopital's,
1 over...
yeah, derivative of the top is 1 over, what's the derivative of that? This is really what I want to see, if you guys remember the derivative of...
5 ln.
Yeah, 5 to the...
ln.
5 to the x.
ln.
5. And then again, that kind of reconfirms what's the only function whose derivative is itself? E to the x, because you get e to the x ln of e. ln of e is 1. That's the only reason that ln piece does not show up for e to the x, right? But it's going to show up for any other base. And what's that, of course?
1 over infinity.
Which is?
0.
0. Cool. So there it's confirmed. It's proven.
1 over infinity.
So this gives us a feel for what might possibly be happening. This kind of thing proves it, right? Now, why couldn't I do what we were saying earlier about just dividing by the highest power of n here, like we did earlier? Just divide it by the highest power of n to see what's going on. Why can't I do that here? Yeah, here this is not polynomial, right? This is exponential, so obviously I can't do it that way. That's why L'Hopital's helps me out here. All right, so let me give you this handout. I wanted to kind of lecture a little bit ahead of the handout, but let me give you this. One more. Okay. So at the very top, I just want to give you a few examples of some actually well-known sequences. Why do you think part A? Look at the triangular numbers. Why would they be called triangular numbers? Why do you think they might be called triangular numbers? Because 1 would be like, there's 1. 3 would be 1, 2, 3, right? 6. 1, 2, 3, 4, 5, 6. You can keep making triangles out of them. Right? So it's amazing. You can ask people, what do you call it? Oh, triangular numbers. Right? So square numbers, you can of course make squares out of them, but you know they're also just squared. So there's two ways to look at that. So pentagonal numbers, you could probably tease out why they might be called pentagonal numbers. That's just fun to say. Say again?
Is that really why they call them that? Because you can make dots?
Yes. It's awesome. Because the idea, the overriding definition of the sequence is just the fact that I got to add one more than I did before, because the fact the base is always going to need one more than it did before, right? So we actually built the sequence up from triangles, and that's why, amazingly enough, we call them triangular numbers. And believe it or not, they do have uses. You could probably imagine, based on like stacking things up in a triangular shape, this kind of thing might come in handy, right? Fibonacci. I don't know. I don't think we've talked about Fibonacci numbers. Who knows about Fibonacci numbers? Anybody? These are these silly, awesome, stupid things. Fibonacci sequence. In my 120 class, I teach like a week of Fibonacci. And basically Fibonacci is just your board. And like you write 1 and 1, and then you say 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. God, I must be freaking bored as hell. Right? You just play with numbers, but then the ratio of one number to the one before it, the limit of that ratio becomes 1.618 blah blah blah, the golden ratio, which is called the golden ratio because civilizations in the past thought that it was related to God, and so a lot of the pyramids of Giza are set up with using that ratio. Frequencies that are played in harmony with each other that are actually elements of this sequence sound good to us. If they're not, they sound bad to us. Art that uses this ratio correctly, it has a line drawn so that the ratio of the sides comes out to be the golden ratio, is more appealing to us than if not. That's kind of freaky shit, right? And here's something else. If you keep making the same, let me see if I remember how to do this. Keep making that same rectangle with all the new rectangles, and you connect all the corners, you come up with that, do I have that on the, I can't remember if I put that on the homework sheet. The chambered Nala shell. Yeah. Right, so Fibonacci is related to how nature builds on itself as things grow. So trees, the tree branches, if you count at a certain level, very often there'll be elements of the sequence if the tree hasn't been cut. Pine cone seeds, all, silly. Black hole frequencies. I don't know. It's crazy. So go to Google and you type in Fibonacci skateboard. And there's actually, I think, somebody, or surfboard. Somebody's created a surfboard that has a curve that's related to the Fibonacci sequence. And supposedly it performs really well, whatever. But it's really freaky. All right, that was a nice side note. So why don't you go ahead and try out those first four pieces, right? Those first four sequences. Write out the first four terms of those. And I've spelled out what we talked about earlier in this limits of sequences. You can either do it the old-fashioned way or L'Hopital's rule, right? So go ahead and try those exercises out on that first side. That's section 11.1, the one that talks about triangular numbers and all that.